Hello, I'm Guilhon. Now in this video, I'm going to show you as a third hands-on activity an application of DFT-F on gallium nitride. So we already performed in a previous video a DFT calculation of this material and show you that instead of 3.2 electron volt, we obtained nearly half of the experimental value. This is a very pathological feature of DFT. The energy gaps and other excitation energies tends to be underestimated. So DFT minus half is a way to obtain good energy gap values with the same computational cost of a standard DFT calculation. So DFT minus half fluxogram is the following. I'm going to talk a little bit more details of each step. You start with the DFT calculations, and then you have to perform an analysis of the orbital character of the top of the valence band, and in some cases, especially for 2D systems, also of the conduction band minimum. And these features will be a basis of some atomic calculations, and the deviation of the constant potential of the atomic systems will be used to determine self-energy correction that must be added on the constant to the potential. But this in periodic systems such as crystals should be streamed with a cutoff rating. And this should be varied, and the cutoff is not adjusted but determined from a variational method. Basically, you're going to maximize the energy gap, and the maximum of the energy gap gives the optimal cutoff. And then we perform it for each test cut. We perform DFT calculations, and then we determine together the optimal cut and then the energy gap calculated by DFT. So in more details, let's go step by step. So we start with DFT calculation. For example, gallium nitride that we already discussed in more details on hands-on activity 1. I'd like to highlight this tag L orbit equals 11. So it tells VAPS to calculate not only the eigenvalues but the atomic orbital of each eigenstate. So this is very important information for the DFT-F application. Everything else stays the same. We might produce an energy band structure like this, and then you're going to check in more details these two states, the green dot and the red dot. For 3D compounds, basically the valence correction stands for almost all the correction that we are interested on. So looking for the valence band, which is band 4 on gamma point. This is a very occupied, and this formation is inside the Procar file, the file of projections on spherical harmonics around each ion. So as you can see, the maximum of the valence band it's derived from the second ion, which is nitrogen, and also especially from the p orbital. So with this information, we see that the maximum of the valence band comes from the nitrogen p orbital, and this information can be directly extracted from from the use of minus half code. Let me just go to the DFT calculation, which should be the one that we you have in this step 1, and we have minus half, and gives you some corrects. And if you look to this command, maximum then maximum character, this should give you directly the proportion of each contribution. So in this material, basically most of the atomic character comes from nitrogen p orbital. Okay, so this is the information we need for now. So this tells us that the correction that must be done from nitrogen gallium should be done on the nitrogen p orbital. Okay, so we are going to neglect for now the other contributions and do a simple correction on p. And this can also be done graphically with some usually called fat bands, and this, as you can see, have the most of atomic contribution comes from nitrogen. Okay, so for example, in this case, we are going to compare the Conshan effective potential from neutral nitrogen and from half ionized nitrogen, removing half electron from p orbital. So the difference from these two atomic calculations, these two DFT calculations, as I show you on hands-on activity 2, is the self-energy correction that should be added on crystal. But it's not directly added, but it a cutoff function should be applied to avoid the interpenetration of self-energy corrections. The cutoff function applied is this one. It has a cutoff distance of cut that should be added. These explanations were proposed on the original DFT-1 paper, but let's say if you have something of similar to this, cutoff should be no big problem, not change very much with the results. Okay, as you have something which looks familiar to it. And so this cutoff should be tested. It should be calculated from different cuts, and for basically looking for this firmization of the band gap with respect to cut. So it starts with the DFT gap, and as we enhances the cut distance, it achieves a maximum, and then again becomes smaller. So this is the optimal region, the maximum band gap with the optimum cutoff. So as you can see, you have to perform some different DFT calculations so to determine the cut. If you like to avoid it, you can start with a good guess of the cutoff parameter. For example, if you look to aluminum nitride, gallium nitride, aluminum nitride, all of them, the maximum of the valence band comes from nitrogen, and you can see that it does not change much if you compare different systems with all the nitrogen atoms, and also with 3D and 2D compounds. This is a very physical quantity, so it does not change much. And well, minus half code is already have an automatic search algorithm, and if you let's say give us a good starting point, it should be not take too much time. And finally, the DFT-F gap and the cut, as I already told you, are determined by this maximization. So when you determine the optimal cut, you in the same time determine the DFT-F energy gap. So all these six steps, okay, the just the DFT calculations, the looking in details from the behavior of the object character, the extraction of these formations, the calculation of the atomic systems, the differentiation, the application of the cutoff functional, the variation of cutoff, and then the maximization of the energy gap. They are already implemented and automated by the -F code. So this is a very special tool for us, and this automatic routing is performed by execute, and basically it only needs this file, this -F dot YAML file. So you have to say which software you are using. The default is VASP, but we wish on the near future to implement for different codes, and how you're going to call VASP with these features. We're going to call VASP with for processors with MPI run, and then the corrections. We are going to perform a simple valence correction, but we might be interested on performing some fractional contributions, corrections, and valence and conduction bands, and all of these different kinds of corrections on DFT corrections. They're implemented and they can be selected by this correction code. So this is a very simple one that I comment. I'm talking about it with you, and some to tell it where the postcard files is, and they -F does all the job, as I can show you right now. So let's go to this folder with podcast generation, but actually -F can do everything in this folder for you. So -F YAML. So this is the file that I showed you before, and on this podcast file, basically you have podcast of gallium, podcast of nitrogen. So these are the files that -F is going to read, and then we call it. You can have some help with this, and he did a great job documenting it. And then we call execute, and then as I show you, it starts with DFT calculations. It makes the corrected podcasts, and then does another DFT calculation. Now change the cut parameter. I hope it finishes quickly. Okay, so it performed the first test. As you can see, I have a current gap very close to the correct value, because -F is also it has some fits that we performed in the past. So if you do not have any idea which value the cutoff should be, please trust the -F initial guess, and then it changes a little bit, and then -F is looking for the optimum cut by maximizing the cutoff with the second decimal until it reaches the set tolerance. Okay, so this is -F, and it's almost finishing, but it should be no need for us to wait until the end of this calculation. So basically the main idea is to the fluxogram of steps, and to tell you that all of them are already implemented and automated by the -F code. So please check it out, read the docs, and use DFT-F. Thank you.